Hey, welcome to part 4 of Models of Growth. We're talking about linear models here. So let's just remind ourselves of what models of growth really means. And it's exactly as it sounds. We've got something in nature or in some practical sense which is changing and growing. And we're trying to model that. So let's look at that word model here. And I think the best definition is it's a mathematical description of some practical situation, and we could have several different mathematical descriptions. It could be a table showing some growth of something, it could be a graph, or it could be a formula. So we're going to do all these things in these coming presentations on models of growth. Right now it's linear, but I think I've helped you here. What's a linear model? Well, it's a linear. Yes. When you plot the data, you get a straight line. So come over here and have a look at that. And what we need to do is to work out, well, what's the best way of plotting a set of data? And then what makes it a straight or linear model or linear model? Let's have a look at that. And a little bit of revision here, I hope. So come on down, and I've got a couple of questions for you. Finding the equation of a line, also called or known as, what makes a line straight? Well, let's have a look at it. I think most people by this stage have seen y equals mx plus c. So we'll use that sort of formula and explain why that describes the equation of a line. And just remember, what is an equation anyway? What does that mean? It means the rule that the points must obey. That's the connection between their x and y values if they lie on this line and be perfectly lined up. Let's analyse that. So starting here, let's have a look. C, if you put x is naught in here, you'll get y equals m times naught is naught plus c. So that means when x is naught, you're looking at this point here, and I'll just do that differently. I'll show you why in a minute. So that would be the point naught c. In this case, that's the point naught 3. Now, what we're going to do is to show how this line grows, thinking about starting at this point. So the y value at this point is c. If we come across 1 in the x, that's just coming across here, and measure the change in y, it goes up by 2. Okay, so at that point, we've got y equals, now the slope is 2. So we've got our our c value, which was 3, and then we're going to have one lot of 2 because x was 1 and the slope was 2. Can you see how it grows? So here, let's just go again. Go one more for x, and it goes another 2. So now it's grown to, the y value's grown to 3 plus 2 lots of the slope. And then if we go another one in the x, it's gone to, the y's gone up to 3 plus 3 lots of the slope. Because the slope is what? The change in y step over x step. Okay, or delta is often used to mean changing in maths, delta y on delta x. So if you change by 1, this is the change in y you would expect. So as you go along, you start at the y-intercept if you like, and then you add on x lots of the slope. Really best understood that way, to see how y grows from a y-intercept with continuing lots of the y-step. Okay, so that's what makes a line straight. You've got to have this lining up every time. Come back over here, and as we go up in 1, to keep it lined up, you must always go up by m. M is 2 here. So this equation would be start at c, and all the y values are x times steps of 2, because the y step over the x step here, or the slope is 2. We don't do it like that. We write it like this, the x term first. But that gives you some idea of the background to straight lines and what you're looking for. What's the answer then? What makes a line straight? a constant slope or m value. Okay, so there you are, and that's how a line grows. Now keep that in mind, because what we need to do is really analyse a straight line and whether it will be a good model for various practical situations. Okay, let's go down now and work on that a little. Here's the first question. When you've got data sets, does it matter? Does what matter? Well, does it matter how you plot these? Which is x and which is y? On the x and y axes, just remember we're using the Cartesian coordinate system, and we call the horizontal axis x and the vertical axis y, and they go in both directions, positive and negative. So what do you put there? Does it matter? Okay, have a look at this one. We've got an angle in degrees and the number of sides of a polygon. Okay, so they've put it that way around. Could it be done the other way? Could you put n up there and a there? Does it matter? Okay, let's answer that question now. Come down and see what the rule is. Okay, the rule. The independent variable has to be on the x-axis or the horizontal axis. The dependent variable is on the y-axis or vertical axis. That's a convention in maths. So we think about this as the independent variable, and as you change it, and we usually talk about going from left to right, as n increases, we think of, this is a polygon, we think of the angle sum, the total interior angle sum, as increasing. Okay, and we think of this angle sum as dependent upon this. Notice it wouldn't work the other way around. If you increase the angle sum along here, would you increase n? That doesn't make sense. Okay, what makes sense is, as you change n, so the other variable, the angle sum, changes. So this is called the dependent variable, and the one down the bottom is the independent variable. And then we've got a formula for it. Notice that this formula doesn't quite look like y equals mx plus c, because it should be something like a equals mn plus c, and we're going to have a look at this example later on. We're just getting our head around some of these ideas of how to plot the graph to start with, and there is a proper way, and the rule is independent and dependent. It's very important that you work out what is responding or what is dependent upon the other one, and choose your axes carefully. Okay, let's go down and have a look at that example. Or we've got a little thing in between here. Medical researchers develop a new drug. So this is a screen clipping from Hayes and Harris Publications, so you should have their book handy by there. They must find the appropriate dose for its job, and that's to reduce the level of histamines in the body. Determine the variables involved and their role. So what's the variable? The thing you're varying, it's a level of histamine and the dose. Now, as you change the dose of this drug, you change the level of histamines in the body. So the dose is independent, and the level of histamine in response or is dependent upon that. So what will you do straight away? You will say, we'll put the dose along here, maybe call it D, and the level of histamine up there. Because according to our convention, the idea is, as you talk about changing this, as you talk about increasing the independent variable, you then say, how is this going to change up here, going up or down? You get the idea. There are some conventions. And please note that when we're talking about the independent variable, we usually talk about D, or the independent variable increasing. Okay, going that way, and then we question what happens to the level of histamine. It's just a convention, so everybody sort of is working the same way, and there's some consistency. Okay, now let's look at that example again of this polygon stuff. So below are diagrams for the first four polygons. You've probably seen this before. A triangle, a quadrilateral, pentagon, etc., and hexagon. So if you count up the number of sides, there they are, and the angle sum in each of those, and you can do that, here it is, by dividing the internal angles into 3 triangles worth, and so on, so you can get this pattern. Now, what's the independent? We've done that. Graph it, and what's the slope, and so on. Let's go through all of these steps now, slowly and carefully with this example. Now, I've shown you the formula. I think you probably already know that from junior maths. So here we are. The angle sum depends on the number of sides. So the number of sides is the independent variable, and the angle sum is dependent upon it. So it's got to be angle sum up there and number of sides here. That's the convention. So I don't know whether you've seen that rule before, but you must discern whether it is an independent or dependent variable. Let's then put the table, and what have we got here? We've got the number of sides and the angle sum. Okay, up there. So from the graph, what can you say? Well, from the graph, you could measure it, an x step of 1, a y step there. What sort of slope do you get? The slope here, of course, is constant, we've said. So on a table, how does that appear? Well, if you go up by 1 in the x, the slope is, well, change in y is 180. So every time you go up by 1, can you see, this is a constant adder, that's often said. But it's really saying it's linear because it's got that constant slope. So every time you go across in the x, you must have a constant y step. And I don't like y's and x's in modelling because we've got axes of a and n. So it should be delta a on delta n, or a step on n step. So in modelling, it's important to refer to the aspects all in terms of the context, not in x and y land. That's what might come off of your calculator, and that might be the theory, but in modelling it must be in the context. So it's got to be angle sum and sides here, a and n. Talk about those things. Okay, so slope is 180, and we've just talked about that. M is the a step over the n step, so doing it like that. Our linear model is, of course, y equals mx plus c. Change it to the context of the question, a and n, and then put the numbers in. So when n is 3, a is 180, so you can put 180 equals 180 times 3 plus c, so c is neg 360. So there's the formula, a is 180, n take 360, done that way. I'll show you how I got the other one in a minute. So the slope interpretation, this is important, you would have done this in junior maths. An increase in one of the number of sides produces an increase of 180 in the angle sum. Okay, so that's important. See that in there? As you increase n by 1, you multiply it by 180, so that goes up by 180. That is the slope value. Okay. Please note here with the graph, you can't join the points because you can't take values in between 3 and 4. Joining points on a graph, let's go back up there and just have a look at that. Joining points on the graph like that suggests you can have a value between 3 and 4. Well, you can't. A polygon has to have a whole number of sides. So therefore we do not join up points here because the data is discrete. You can have 3, 4, 5, 6 sides. You can't have 6.5. So just note that subtlety with your graph as well. So here we can't have n less than 3 because it wouldn't be a closed figure. A polygon is poly means many-sided plane figure, and it's got to have it's got to be connected to make a figure out of it. Okay, so let's have a look at the other one I did up above. I said the angle sum was n take 2 by 180. Now that's doing it from the number of triangles. Number of triangles is 1 less than number of sides. If we expanded that, that's 180n take 360. So it agrees. This formula is looking more at the geometry, and what we've done over here, come over here again, that formula is based on mx plus c. Being very just clinical about our maths, finding the slope and then putting it in front of the independent variable and adding our constant. Okay, so hopefully you've seen some of that before with finding y equals mx plus c. All right, come down, I've got some for you, just a few to warm you up here on revision of equation of a straight line. So there's question 1. I'll show you the answers in a minute, so have a go at question 1. You can use your calculator to help you look at the graph if you wish, but you must be able to draw it on a piece of paper with appropriate scales. And just keep in mind, the graph will usually only be in the first quadrant, positives, because we're talking about modelling, and it's fairly rare to have a practical situation where you're involving negatives, maybe temperature and stuff like that. But you must have a scale here, and you must label it. These could be 5s or whatever, so label that. You must label the axes in the context of the model, and all of that is just worth 1 mark. Then you've got to plot it correctly and talk about any features. So you must be very accurate with your graphical model here, labelling axes and label them and the scale and plotting accurately here. Okay, that's important. All right, so have a go at that one and have a look at the answer in a minute. Let's go down to question 2. Question 2 is setting up a table, and have a think about that one. Converting speed in commas now to meters per second. A little bit of help over here. Okay, let's go to question 3. Okay, 3 and part of 4. Okay, this is interesting. What would be the dependent and independent variable here? Would it matter? Okay, question 4. Okay, same thing, choose carefully. And question 5. Okay, so that's all we've got there for this revision of the linear modelling or linear functions, straight line graphs if you like. Let's have a look at the answers. Here we are, question 1, most of it. Did you join up the dots? Is it appropriate? It is, isn't it? Question 2 and 3. And question 4, most of it. And the last bit. And then question 5. Okay, so think about that. You might have to revise that finding the equation of a line. It's assumed here y equals mx plus c. See what you think. Anyway, I'll be back with another presentation or several of them in models of growth. So I'll catch you then. Cheers for now.